So, good evening, ladies and gentlemen. Thank you very much for being here today. I would like to thank the organizing committee for this special opportunity of giving this talk, which I title Bondi Accretion for Non-Isothermal Flows onto Supermassive Black Holes with an Accretion Disk. This is work I haven't done alone, but with the help of special people, Jaime Clapp from the Nuclear Research Institution in Mexico, Leonardo Sigalotti at University One in Mexico as well, Professor Ruslan Gabasov, and Professor Ernesto Contreras in the University of San Francisco in Quito, Ecuador. So I think I can put this like this, right? Yes. So here's a brief outline of the talk. I want to give some motivations about why this is an interesting topic in astrophysics, followed by some results coming from the classical Bondi 1952 paper, then presenting some isothermal case with gamma equal to 1, followed by how we add electron scattering and spectral lines in addition to solve the equation with gamma different from 1 to finally show some results and some observables we think are interesting to see. Okay. So what is accretion? This definition gives us a good start. In astrophysics, accretion is the accumulation of particles into a massive object by gravitationally attracting more matter, typically gaseous matter, in an accretion disk. Most astrophysical objects, such as galaxies, stars, and planets, are formed by accretion processes. Then I found this slide in the internet from a lecture of Professor Andrew King, where a bit of more information can be added to our initial definition. We have a central object here, massive central object, and define accretion as the release of gravitational energy from infalling matter, where energy is released usually in the form of electromagnetic radiation. So accretion is playing a major role in several kinds of astrophysical systems, such as X-ray binaries, supermassive black holes in the center of galaxies. Very important to understand gravitational and magnetic fields. Everything in close correlation with galaxy evolution theories and, in the end, large structure of the universe. In his seminal work on spherical accretion, Bondi in 1952 established the fundamentals to begin to understand the steady-state equations, stability and energetic arguments to impose upon the accretion rate. Probably a worth to notice general summary of this work is the two extremes where the accretion rate somehow move. In one hand, whenever the relative velocity star cloud is larger than the sound speed, the dynamical effects are the regulators, whereas the speed of sound is larger than this velocity, then it is the temperature, the main regulator of the system. And the final value of the rate will somehow depend on what part of the regime we are interested on. Here is the configuration we are studying. A spherical cloud with pressure and density very far from the system. I believe it's a bit better like this because I can move the mouse and having actually this freedom. So I'll do this. So a spherical cloud with pressure and density far away from the massive object with the relationship between them given by this polytropic proportionality, with indices between 1 and 5/3. The mathematical system to solve is given by the continuity and momentum equations, resulting in two equations with two variables. Of course, in the case of Bondi 1952, only considering gravity. So, after fiducial definitions and to write down dimensionless equations, we arrive at these two. First, this parameter here is called accretion rate parameter, key in the finding of physical solutions. These two functions, depending only on the Mach number and the normalized distance, are special functions with special properties. And the connection between them is made through this capital lambda built with the accretion parameter and the polytropic indices in the way is shown in this little oval here. This slide briefly gives us a sense that these two, f as a function of the distance and g as a function of the Mach number, have minimums from where we are able to define a critical value for the accretion parameter. In the specific case of these two plots, calculated and visualized with a gamma equal to 7/5. I have remade the 1952 versions to give a sense of the different kind of solutions that we are obtaining depending on the value of lambda. Here is the Mach number as a function of the distance for three different values of lambda. 4 critical values, 1/4, and exactly at the value of the critical number we gave before. In the particular case of Bondi 1952, with the special notation of type 1 and type 2, he is able to classify several kinds of flows, which I don't go into detail for the lack of time, but using energetic arguments, it is the type 2 flow, this one shown here, the most likely solution presented in this accretion system. One last slide regarding this purely gravitational system, and one point I think is worth to mention. And this is when the gamma is equal to 5/3. In this case, the fast summary is that there is no sonic radio. Okay, now we turn into our specific problem with the addition of an accretion disk around the massive object producing the accretion. And in addition to the gravity, we also add two radiative forces, particularly electron scattering and radiative forces coming from the absorption of spectral lines. So, to begin with, I would like to mention this work from Ciotti and Pellegrini 2017, where they do calculations very specifically analytical because they are using gamma equal to 1, which means isothermal flows, and found useful ways to add electron scattering and present steady-state solutions for few galaxy models. So this is our plan. We have combined the geometric effects and assumptions by PROGA 2007 to compute the radiation field from the disk and the central object with the semi-analytical solution procedure provided by Ciotti, Pellegrini, and company, motivated somehow from a work we did before in a SPH simulations where we actually need proper and good, initial conditions to begin the simulations at the evolution of the system. In order to do that, we add, as I mentioned before, electron scattering in addition to force coming from absorption lines. So in the momentum equations, we add this term. In the case of the group of Ciotti, Pellegrini, and company, they add only electron scattering. We also add, in addition to that, forces coming from the absorption of spectral lines. Here, I just wanted to show how the solution looks like for this kind of flow and the classification of solutions we will use in a few slides ahead. So we have here the Mach number, and this is the distance. So for instance, in this case, this solution here will be called type 1. This one here will be called type 2. This is going to be relevant for us 2 or 3 slides ahead. Type 5 solution, type 3, type 6, and type 4. Here is another modification we made. We now include the angular dependency in the nominal number of the accretion rate through this F here, accounting for the solid angle covered by specific streamlines in the flow. We can see that whenever this dependency does not exist, we recover the classical Bondi result, exactly equal to 1. We estimate that this F is going to be less than 1, a bit smaller, for radiative angular dependent processes, which is our case in this work. So in order to have transonic solutions, we request this parameter to be the critical number. For the pure gravitational case, being this one here, this factor. Our contribution is coming in addition to that factor from this term we are calling radiative term, which I describe in the slide, in the next slide. The structure of this radiative term is shown here. We can easily see both contributions. Here we have the Eddington luminosity, and whenever we put this term called force multiplier accounting for lines equal to 0, we only are accounting for electron scattering coming from the accretion disk. If we want to add spectral lines, then we switch this term on and having the contribution from line. All the mathematical details are in this paper, Ramírez-Velásquez 2019, and also based on the PROGA 2007 paper I mentioned before. Finally, some of the models were wrong using this radiative term. Something I had to be very careful is the existence of this critical angle here, for which there is a transition from physical solutions whenever the value is above 0 to type 5 solutions not considered physical whenever you have this term below 0. The different models are here with and without line, saying that we have both electron scattering and line or not. And also the fraction of luminosity coming from the central object, usually in the form of X-ray, and the fraction of luminosity coming from the accretion disk, usually in the form of UV emission. Our results are given all in terms of the match number for the different models. Stars, meaning the contribution of spectral lines is on, and 1 and 2 and 3, changing the different fractions of contribution between the central object and the accretion disk, where we are able to explore the influence of the radiative forces in the calculation of the critical radius. And, of course, it influence in the velocity profiles. For instance, it is easy to see how the increase of the fraction, because we are increasing here the fraction of the radiation coming from the disk, push away the sonic radio, changing the whole structure of the flow. Here are the density profile of our solution, with line and without line. Here the star is line, and here this is without line. Where we have interpreted a change in the volume occupied by the gas coming, of course, from the change in density, depending on the kind of radiation shining upon the gas. Before finish, I wanted to mention this novel idea about looking at the symmetry in absorption lines in X-ray spectra of compact objects to unlock important features of the flow. So I'm just presenting few of them, a very small catalog of symmetry in lines. We are imagining the falling of an atom that has a transition at 10 Armstrong, and the differences in symmetry are coming from changes in the fraction of contribution between the central object and the accretion disk. One last thing before giving conclusions is this concept of accretion bias. The general idea is that whenever you introduce density and temperature coming from finite radius into the assumption of rho and T at infinity, in the mass accretion definition, you will find an underestimation of the boundary radius. Boundary radius defined as the radio where the accretion is to consider to be significant enough. These numbers are usually around from 30% to more or less 90%. So I only extract 3 conclusions to present here, but you can find the other conclusions in the paper. I can facilitate or give you the link or the material itself, but we can extract some of the information from these 3 slides. When the radiation force due to spectral lines does not contribute to the heating, pure gravitational accretion onto a supermassive black hole occurs when the X-ray emission intensity is strong and participate to the same degree as the UV emission. As long as the UV emission dominates the X-ray heating, a transition from pure accretion to mathematical but non-trivial physical type 5 flows occur. So this is something we have to be very careful whenever you are looking for solutions angular dependent. As the UV emission becomes stronger, the gas density close to the center becomes higher. The same trend also applies to the case where the line driving is not considered, except when the X-ray luminosity is strong enough to suppress the outflow. In this case, only pure accretion takes place and the central density achieves much higher value than the other models. And a third and last point I would like to mention, not sure how much time do I have left, is X-ray absorption lines might help to unlock some of the special features of these flows around supermassive black holes. Thank you very much.